to be louder. That's it. That's easy for me. Welcome to our second WVC Speaks Open Lecture Series. So this is our second. And I wanted to share with you the dual purposes of this lecture series. First, to create a forum for a dynamic, inclusive community of intellectual sharing, which enables both faculty and staff to share their expertise and passion for their subject matter with their colleagues, all of us, and also our invited guests from other campuses and our community. And secondly, to create opportunities to present a wide range of academic and topical presentations led by faculty and staff, and explore and celebrate the breadth of knowledge and experience here in the WVC community. So again, thank you very much for participating. We will have additional lectures throughout the rest of the school year. I'm getting some feedback, I think. I am pleased to introduce Dr. Ralph Dawes. Dr. Dawes has a PhD in geology from the University of Washington in Seattle. He has taught physical geology and environmental geology for the past 23 years, the last 16 here at WVC. He is passionate about sharing how the geologic history of the Pacific Northwest gives insights into the landslides, floods, volcanic eruptions, and earthquakes of today. So please join me in welcoming Dr. Ralph Dawes.
Is that going to get my voice? That works? Okay. All right. Thank you, Kelsey. I have to use my wireless mouse. So let me get started here. All right, well, welcome. Thank you for coming. Thank you for that nice introduction. Yeah, so the topic today is earthquakes in Washington in particular, is what I'm going to focus on, Washington State. Is the coast really toast? Okay. And then we're going to bring it all the way over to this side of the state and also address what about Wenatchee? Okay. And in doing this, laser pointer. I'm going to break the state up into 3 regions. And then we'll discuss somewhat separately from each other because they each have their own exposure to different kinds of earthquake hazards in their own way. So one is the coast, which is out here on the actual open Pacific Ocean. This area in here that comes part way up the Columbia River, but not too far, and probably up the Strait of Juan, but basically out on the coast. And then the Puget Sound region in here, which includes Seattle, we're going to separate that from the open coast out here. And then there's Eastern Washington, which includes Wenatchee, which will be the 3rd zone that we'll look at in terms of earthquake hazards. And by the way, when my wife and I moved from Seattle to Eastern Washington about 16 years ago, we were surprised to find that we were called coasties. Because in our thinking that was out here, but we realized, the ocean does come in here and Puget Sound. But for the purpose of this talk, we're keeping the coast separate from the Puget Sound region. Not just because my wife and I are used to that, but for geological reasons. And I am a geologist primarily by scientific training, so much of my approach is going to be looking at what the geological evidence is that has led to this more recent understanding of what the earthquake hazards are in the Pacific Northwest. Because most of the discoveries and most of the revised knowledge we have now does come from geology and also other earth sciences like seismology and so on, but I'll be focusing on the geology aspect. So let's see. So then the highest, I think, point in raised concern or interest and awareness of the hazard of earthquakes, what the threat is to the Pacific Northwest, particularly out along the coast, is from this article by Catherine Schultz last summer in the New Yorker magazine. That really got a lot of attention and discussion. And the name of it is a really big one, in the actual magazine. And that's her term for these really huge earthquakes that happen in certain settings, like out on the Pacific Northwest coast. She also uses the term big one for them almost as big, but not quite so widespread that possibly devastating earthquakes. I'll occasionally use slightly more technical terms for those types of earthquakes. but I'll use those too. And here's probably the most shared quote from within her article, which is that our operating assumption is that everything west of Interstate 5 will be toast. That's the extreme statement. From Kenneth Murphy, FEMA director for the region that includes Washington State. Now, FEMA was involved as one of the agencies in this report down below, and there's a number of reports like this, to take a more thorough, careful, balanced view. And here's an example, maybe balancing quote compared to what Kenneth Murphy said, I think off the cuff, which is that the number of deaths for this type of earthquake we're talking about, Catherine Schultz is a really big one, could exceed 10,000 people, more than 30,000 people could be injured. The economic losses have been estimated upwards of 70 billion. The potential consequences of a great Cascadia quake are sobering, and one will happen eventually is the point of our article, and I would agree with that. And I'll show you the reasons for thinking so. But let me just jump to what I'll summarize with later, but with more detail perhaps, is that the coast is at risk for and will eventually experience magnitude 7.5 to 9 earthquakes. Now the 9 is the really big one, and that's a somewhat approximate number. It could go above 9, although that doesn't often happen. And then the Seattle Puget Sound area and the earth underneath that area, earthquakes magnitude 6 to 7.5 will continue to be generated. Several of those have already happened historically in the last 100 years, as I'll point out. But there's more of a risk to earthquakes within the Puget Sound region than we realized before the 1990s that we know about now. So to add to that consideration. And then the Wenatchee and Eastern Washington area has its own faults. We'll talk about how faults are related to earthquakes. Geological faults that have more earthquakes up to magnitude 7 or even higher than used to be realized. So that's also based upon more and more knowledge we've gained in the last 30 years or less. So we'll talk about that as well. So I was using those magnitude numbers. That's a way. The magnitude scale is a way of expressing the power or energy released by an earthquake. It's actually the total energy. And so here's a pretty complicated graphic illustrating some of that. Now here's the energy release in these earthquakes of these different magnitudes over here. That's a capital M number I'm using for magnitude. Technically it's the moment magnitude scale, but I'm just going to call it magnitude. You can see it goes up not in a linear way. It really goes up to huge amounts of energies as you reach to higher magnitudes. And also, it's the small earthquakes that are common. And it's below 3 to 2, people don't even feel these earthquakes, even if they happen right under them, once they're down below about 2.5. When you get up to the magnitude 9 earthquakes, they're not so common. They don't so these numbers in the middle, over 1 million of the little earthquakes that people don't even feel happen around the world every year. But the magnitude 9 ones, the really big ones, they happen less than once a decade around the world. And 2 examples on here that are 9 or above, 9.0 or above, are Alaska 1964 and Chile 1960, and those are in settings just like the Pacific Northwest coast, which is the kind of place that can produce earthquakes like that. So, and there's some other historic ones on here, San Francisco 1906, high up above 7, a little bit towards 8, and so on. It's a lot of energy released in these higher magnitude earthquakes. So let's see. There we go. So, has anyone here experienced an earthquake? Probably quite a few of you have. Maybe just about all of us. Yeah, so what was...
I got one yesterday.
Yesterday?
I was discussing your book.
Really?
Yeah.
Where was this at?
It was, I'm afraid this was happening. I'm sorry.
That's okay, I understand. Well, was it a kind of small earthquake? Small?
Yeah,
A tremor? Okay, so little earthquakes are pretty common, and around here, they're particularly common up towards Intiat and Chelan. As one area, we get a lot of them, but people in the area actually feel something like once a year up in that area. You don't, Wenatchee doesn't get felt earthquakes that often. So if you don't live in an area that gets felt earthquakes every year or two or three, you may not be aware how much they happen, the little ones, in other places. And we're going to talk about, now that may not be where you felt an earthquake, but we're going to talk about that in the Chelan zone. Has anyone been in a pretty bigger earthquake?
In Japan.
Oh, in Japan.
I lived in Japan, and I rode over a wave that came through the living room and out the door.
Yeah, see, the earth itself was moving in waves. Yeah, that's what the big ones can do. Yeah.
In 1990, Whittier earthquake in California?
Oh, the Whittier earthquake, Southern California.
Yeah.
That cause things to fall off the shelves, that sort of thing. Yeah.
Mm-hmm.
Yeah. Well, another example.
I was in that same earthquake
Go ahead.
in California growing up.
So yeah, California gets, especially along the San Andreas greater fault zone, quite a few earthquakes. Susan, you had one?
Yeah, Loma Prieta.
Oh, Loma Prieta. So where exactly were you when?
About a mile and a half from the epicenter.
That was in 1989.
Yeah.
That one right before the World Series game was about to start between San Francisco and Oakland. Yeah, that was a serious earthquake. Okay, well, we're not going to. The California earthquake story is a little bit different, except for the very northern California that reaches into the zone we're talking about. So we're going to focus on the Pacific Northwest.
Ralph,
Yeah.
when I was showing Woody on as a presidential candidate, the campus, when the Squally earthquake
yeah.
happened, and I was outside of Beecher Hall, and the oak trees were moving like this. And I thought, where do I take this man to be safe?
See, and that raises the point. Big earthquakes in western Washington, what risk are we at for the effects of those if they get big enough? Because we feel some of them over here too. Okay, well, I'm going to move on. Here's a quote here from Charles Darwin, who experienced at a slight distance one of these megathrust or really big earthquakes down off of Chile when he was on that trip around the world in the Beagle as a younger man. And he was more of a geologist in those days. He became more of a biologist as time went on. But here's a quote from his journal. "A bad earthquake at once destroys our oldest associations. The earth," this Victorian language, I like it, the very emblem of solidity has moved beneath our feet like a thin crust over a fluid. And then 1 second of time creates in the mind a strange idea of insecurity, which hours of reflection will not have produced. So when you feel a serious earthquake that sends waves underneath you and moves things around and knocks things off shelves, or worse, yeah, it changes your view of the earth as a solid object. And again, down in Chile, that's the same kind of setting along the coast that we have on our Pacific Northwest coast. So what is an earthquake? Well, earthquakes, as I'm going to talk about them, are produced by the earth on what are called faults, which are more or less planar surfaces that cut through the earth. So this is supposed to show a fault plane cutting down into the earth. By the way, this is maybe an old graphic. These are supposed to be cars. Back when they were more square. And so this fault plane cuts down through the earth, and the rocks on either side are stressed and trying to move in opposite directions. And when it ruptures, that's an earthquake up here. So it starts to break here at the center, at the beginning of the earthquake. That's the hypocenter, where the earthquake moves the most and the fastest and at the start. And that's down in the ground. And then the whole rupture surface is how much of the fault actually shifted. So on one side moves relative to the other side along the fault. One big mass of rock or slab of rock moves relative to the other side. And so the hypocenter is the center of where the earthquake occurs underneath, but there's a larger rupture surface where the whole thing moves. And the epicenter is the point on the Earth's surface up above that you can see on the map. But the earthquake itself happens at some depth. A little bit more theoretical detail, that the rocks of the Earth are behaving according to elastic rebound theory. This was first developed and applied to create a workable earthquake theory following the 1906 Great San Francisco earthquake, with the elastic rebound theory. And it still holds up as a basic story that seems to be correct. So the faults are here's a fault cutting through vertically this patch of land with a fence that goes across it. It's getting sheared or pushed in opposite directions on either side of the fault. but the rocks haven't broken yet. The fault is locked and they're building up stress, building up all this push energy, and they're bending. And finally, they rupture, they fail. That's the earthquake. The earthquake is produced when the rupture happens. And then the rocks shift back to essentially the same shape they had before. That's the elastic rebound. Okay? So as long as the fault is locked, but the rocks are trying to move and are moving, but they're moving without breaking yet, that means it's building up towards the next earthquake. And earthquake waves, I'm not going to go into these details, but the earthquake releases this energy in the earth in the form of waves traveling out. They move through the Earth's interior, and then they hit the Earth's surface, these waves of energy of moving Earth, and they generate another set of waves at the surface known as surface waves. And those usually move the Earth's surface the most, as the surface waves themselves. And they move through different kinds of material differently. If a part of the Earth's surface that has a lot of soft sediment that goes down for some depth is going to shake a lot more from the surface waves in particular than solid rock right underground. Okay, so that's why, like in this Quella earthquake 2001, some parts of Wenatchee and the valley felt it, depending on what you were on and where you were, and some parts didn't, because what's under the ground also affects how much the waves shake things, and certain types of ground will amplify those waves. Cities tend to be built in places that have ground like that. We'll talk about that. Yeah.
Who's the geologist in the rebound?
It's one of those notes I forgot to look up. I know his name, but I don't have it in my head right now. He's a famous.
Berkeley seismologist?
No, this is 1906, and it's a famous name in geology. I think he worked for the USGS Survey, or maybe he was even for Europe or something. Anyway, so I should know, and I just forgot, because I'm not doing the San Andreas fault earthquakes. But at least to geologists, it's a well-known name, and I'll just have to look it up later. I haven't heard it, it's not ringing a bell yet. Okay, so what causes all that stress in the Earth's surface layers, crust, that leads to earthquakes? For the most part, it's plate tectonics. So we're going to focus on that as the driving cause behind what makes these faults break and what makes these earthquakes happen. So here's a map from the USGS Survey. It's a little bit modified with these arrows, but of the major tectonic plates of the world. You see the Earth has this outer layer known as the lithosphere that consists of these giant plates, slabs of rock, tens to over 100 miles thick and up to thousands of miles across. These are the tectonic plates, and they're all moving. They're moving. The movement is driven by heat working its way out from the Earth's interior. So since all these slabs of rock are moving, wherever they meet up with each other, they're interacting with each other in a very stressful way. They're either pulling apart, diverging, or they're pushing together, converging, or they're sliding side by side in opposite directions. Three basic ways that moving plates can interact along the boundaries. So much, if that's correct, then most of the world's earthquakes, at least a large number of them, will be along the plate boundaries. Okay? By the way, here's our little, it just makes the cut to me on this scale of a map. The one that you could play off the Pacific Northwest here. Here's Vancouver Island, Puget Sound. So we have a somewhat small tectonic plate right off our Pacific Northwest shore here, and they don't show the arrows, but it's coming in towards North America. So here's a little bit more about plate tectonic theory, just in general. So here's where two plates are moving apart, divergent plate boundaries. Yeah, they're spreading. Like this, here's an example there. Plates are moving in opposite directions. The plates move off, and over here, this plate is encountering another plate that happens to have a continent on top of it. And this plate that's spread away here has oceanic crust on it that forms at the spreading boundary. And that makes it a thin, dense plate relative to the one with continental crust. So this one goes down, and actually it's dense enough to go back down into the mantle and subduct. The word for it. So this is a subduction zone. This is like the Pacific Northwest. We have an oceanic plate coming in from a spreading center offshore, spreading ridge offshore, and it's encountering North America and it's going down underneath. So that's a convergent plate boundary, and here's the subduction zone from there to the, and it produces a chain of volcanoes. The subduction process causes magma to form and so on. I'm not going to talk about volcanoes, except this is what leads to the Pacific Ring of Fire. It's these chains of volcanoes that just about ring around the Pacific Ocean. They're all along subduction zones like this. These are also, as we'll see, earthquake zones. And then I guess we don't need to get into the kind of plate boundaries here too much. So here's earthquake epicenters, magnitude over 4.5 over just a 10-year interval, just plotted up on a map of the world. you can see they follow these patterns, and they basically, you can trace out where most of the earthquakes are, and that's the plate boundaries. So it's the plate tectonics that causes most of the earthquakes. And most of the earthquakes are near the plate boundaries or right along them. However, here in the Pacific Northwest, during this 10-year interval a few decades ago, not so much, because there's a plate boundary all along the coast here. And that lack of, in 10 or 20 or 50 years even, a lot of earthquake activity along our plate boundary, which doesn't really show up here on the earthquakes, led to the idea that we were safe as far as these giant earthquakes go, because we had some sort of special subduction zone. We didn't know, but we had no historic record of major earthquakes, and once we had seismometers measuring things, we were not getting these major earthquakes on our subduction zone, which is called Cascadia, the one here along the Pacific Northwest. So they were trying, geologists and other scientists were trying to figure out, why don't we get those earthquakes here? Is it extra slippery somehow? It's a little bit slower than most other subduction zones, the rate at which the plate is going down. They weren't sure. Well, it turns out we do, they just don't happen all that often. So we're going to talk about how that came to be discovered and how that has shifted our whole thinking. And that's what that article by Catherine Schultz was about, although we've known this for more than 20 years now, that we do get those big earthquakes. We just don't get them as often as some of the other subduction zones. So here's the Pacific Northwest in more detail. Here's the chain of volcanoes caused by the subduction, the Cascade volcanoes. It's a little bit hard to see, but this black line here where the arrows come together is the plate boundary. And then this little set of oceanic plates, which we can lump together, they're all moving essentially the same way. We can lump them together as one Fuca plate. It's coming in from offshore and it's going underneath North America, a little ways offshore. So that's our Cascadia subduction zone in here. And the worst kind of earthquake, or the biggest kind, I should say, I'm not to be judgmental, doing science here, is when this whole thing becomes a fault and all fails at once. And that apparently has happened in the past. Those are the really big ones. You can also fail along part of it. So here's an even closer look. So we got the Earth cut away here, so we can see inside the Earth, in this schematic. So here's the one big plate coming and subducting. Here's a North American plate on top of it. And so North America's have material added, scraped off or slabbed and accreted off of this plate going down to make the accretionary prism. But North America goes out to here. And then this part of the plate boundary, the beginning of the subduction zone, is locked. It's a giant fault, essentially, that hasn't moved in a while. So that, and it runs along the coast from Vancouver Island to California, northern California. So you have this giant locked fault, which means, and things are getting stressed, and the rocks are getting pushed out to ways on the other side. So that's building towards the next big earthquake. There's ways of measuring how it's locked. Show one other picture. Okay, so here's another graphic, a map of the Pacific Northwest coast. There's this approach to studying the Earth called geodesy, where you measure exact locations and how they're shifting. In this case, using GPS stations that are anchored in the bedrock at these different locations. So over the course of several years, they add up how these parts of the Earth's crust are moving, and they turn them into these arrows. The longer the arrow, the faster it's moving, and it shows you which direction these parts of the crust are moving. So it turns out, it's not just the one Fuca plate coming in like this. There's also some effect from the San Andreas, which is a transform, a sideways plate boundary down in California. It's pushing up, part of California down here is pushing up this way along the coast, and that's adding stress that's making the whole Northwest rotate like this out on the coastal zone. And what's happening inland in Nevada and so on is also adding a component that comes up and is helping rotate. There's evidence this type of rotation along the coast has been happening, and that's normal. You can see it happening year by year, even month by month from these GPS stations. This is stress building up. This stuff is moving, but the main fault out here hasn't broken since they've been measuring this. They can also measure the vertical motions as well. So anyway, there's a lot to the plate tectonics. The one Fuca plate coming in, and the California San Andreas effect is all the way up to the Pacific Northwest as well, to add another component of the stress, apparently, which helps explain which way the faults and earthquakes go when we get to the Puget Sound area as well. So, all right, so we're gonna have to break down the areas of where the faults are that the earthquakes occur in the Pacific Northwest to beneath the coast, that big megathrust fault. Thrust fault is where one slab of rock goes beneath the other and the other one climbs up on top of it. That's like a subduction zone, so that's just a giant thrust fault out there at the beginning of the subduction zone, a megathrust fault. And that can produce earthquakes of the biggest type up to magnitude 9, or possibly even higher. Great subduction zone earthquakes, the really big ones. Now beneath the Puget Sound lowland, or the Puget Sound region, well, I forgot to show you that there's, maybe I can back up a little bit. If you get under Puget Sound, all right, so here's Puget Sound, the whole region here. Down here, there's more slippage by the plate going down, but nonetheless, there's some things going on down there where smaller areas are locked. And we talk about more causes of earthquakes down here, but it's basically just smaller locked areas. But they can produce up to magnitude 7 or even a bit higher earthquakes, and they do down deep under Puget Sound country. Those are the deep earthquakes that happen under Puget Sound in that greater lowland area. And Nisqually 2001 was an example of one of those. So yeah, Ken.
With your megathrust earthquakes, is that, when that breaks loose, is that a reverse fault?
It is, well, a thrust fault is essentially a reverse fault, but at a kind of a low angle.
Well,
Yeah, so depending on which part you're looking at and what the angle is, it's a thrust or reverse fault. For the most part, it starts off pretty low angle and it's a thrust fault.
okay, thank you.
All right, so those are the deep earthquakes. Anyway, these have happened historically several times in the Seattle and Puget Sound area, the deep ones. There are also shallow faults up in the crust beneath the Puget Sound region, sticking with Washington State. And it turns out they can produce significant earthquakes up to magnitude 7.5. And because they're shallow, that gets a lot more energy up to the surface quickly before it dissipates over a broader area. So in some ways, if you're right on top of a magnitude 7.5, well, if it's the same magnitude that is right underneath you, just a mile or 2 or 5, that is likely to do a lot more shaking and damage than if it's down 20 miles. So the shallow ones for the same magnitude are typically worse over around the epicenter area. At least they shake more, potentially cause worse damage. And then beneath eastern Washington, we only have the shallow crustal faults here in eastern Washington, but we do have them, and it turns out we have a number of active ones, more so than we knew 30 years ago. And based on some studies lately, we're getting more and more confident that they can go up to magnitude, well, we already knew this kind of, but we're getting more details about it, that they can go up to around magnitude 9, maybe even a bit higher, the ones in eastern Washington. Here's a diagram showing what I was talking about. So here's the megathrust earthquakes, the really big ones out at the beginning of the subduction zone and under the coast. They happen in this zone. Okay, the last one was 1700. We'll talk about that. That was that discovery started in the 1990s. The deep earthquakes are under here, further down the subduction zone, underneath a little more inland, like the Puget Sound country. Shallow crustal earthquakes happen in the Puget Sound country, like there's a fault here called the Seattle Fault. That's an example of a shallow crustal fault up here in the continental crust. And there are shallow crustal faults in eastern Washington, like the one that produced an earthquake in 1872, which we'll talk about as an example. But let's start with the coastal earthquakes, the really big ones, like Catherine Schultz's article was about. And one way to get a handle on what they're like and what they can do is to look at other examples that have happened in more recent history, like could happen in some overlapping ways with our Pacific Northwest coast. So there's Alaska 1964, that was magnitude 9.2. Indonesia 2000, some of you may remember Alaska 1964. Indonesia 2004, on Boxing Day, the day after Christmas. That was, I mean, look at the total fatalities, between 200 and 300,000. And I haven't mentioned yet, but that was largely caused by this thing called a tsunami, which is this giant set of surging waves. But the waves are such long wavelengths, they're more like a surge of the ocean than you would think of as a wave normally. Anyway, these tsunamis, in each case, the fatalities, over half of them were caused by the tsunami, the waves that washed ashore afterwards. And most of the ones from Indonesia, too. In fact, I did a little extra looking up numbers. This is, the last two columns are how far away the furthest fatality caused by the tsunami from that earthquake occurred in miles approximately. And a little bit of detail over here. So Alaska in 1964 killed 12 people in Northern California. I think they were all in Crescent City, 1,600 miles away by the tsunami that came down across that much of the Pacific Ocean. Indonesia 2004, people in the northeast coast of South Africa were killed. 4,800 miles away across the Indian Ocean. And Japan 2011, you know, the one person got swept away to his death when the waves surged up and took him from a shore down into Northern California outside Crescent City. So one death in North America from that tsunami, 4,600 miles away. The point is, on these biggest earthquakes, the tsunamis can cross whole oceans, as well as the more local damage where they climb up higher and are more threatening. But you know, look at the range of fatalities. Alaska 1964, 139. Indonesia 2004, 250,000 is quite variable. Depends on a number of things, including the population along the coast. Here's a little bit more about how those subductions, great subduction zone earthquakes work, and you can see how they produce tsunami when they shake the ocean floor. So, all right, so here's a subduction zone. The oceanic plate is going down. They put it underneath the continent on this plate, on the overriding plate. So as time goes by and the subduction zone megathrust fault is locked or stuck, it nonetheless stress this convergence and is causing the overlying plate to go down here and up here. It's deforming. Okay, but the fault hasn't released yet. Building up its elastic potential. Finally, when it does break, the fault ruptures and comes unstuck. This part of the plate comes back up of the overriding plate, and this part sinks back down to where it was before. So after one of these great earthquakes in these subduction zones, parts of the coast go up and parts of the coast go down. It just depends on where you are relative to this, where you're looking at relative to this motion. So this is Turnagain Heights, on the outskirts of Anchorage, Alaska. It has this really weak layer in the ground that really broke apart during the great 1964 earthquake, which was a couple hundred miles or 150 miles away in Alaska. Anyway, so, you know, you can imagine, and you've probably seen some of the videos and pictures, how earthquakes like this cause their damage. There's the ground shaking to begin with, the earthquake itself. Then the great subduction zone earthquakes shake the floor of the ocean, and once they're above magnitude 7 to 8, that's usually going to produce tsunami. Another thing that can happen is when the Earth is behaving like with waves and experiencing those seismic waves, certain types of ground will essentially liquefy, like quicksand. And so you get liquefaction where buildings can sink or tilt, that sort of thing, roads break apart. The ground can crack, and that's part of what happened here. Landslides get set off, and there's a bunch of other secondary effects that get at, you know, buildings and infrastructure and so on. Fires are common. If it's a really major earthquake and buildings get broken and pipes get broken and electric wires get broken and natural gas pipes get broken, you can imagine fires happen. The Japan earthquake 2011 broke a dam that made a major flood, and that was a big problem among its effects. So all these things could happen from these really big, around magnitude 9, great subduction zone earthquakes. Okay, here's tsunami. This is Japan 2011, a couple different pictures in different locations of the tsunami coming down. By the way, tsunamis are multiple waves. They can take tens of minutes or more for each crest to come in, and it may take hours for the whole tsunami to be done. They're not one quick surfing wave breaking. And also, a lot of people don't know, unless they learn about tsunamis, that it's multiple waves. The first one isn't usually the last one. So don't rush back down there after the first wave. That happens. And this is afterwards, a town on the coast of Japan that was, most of this is from the tsunami, most of the damage that the people are standing in the middle of afterwards. All right. Now, let's look at, you know, these higher, more powerful types of earthquakes that we have a history of happening in the Pacific Northwest. You have to go back, so the Cascadia subduction zone, the last major around magnitude 9 earthquake there was 1700. That comes from the geological evidence. Nobody was writing down any written records who lived in this area back then. We have to reconstruct it with modern evidence. The Seattle fault, Seattle-Bremerton fault, it's sometimes called, had around magnitude 7, maybe a bit higher, probably a bit higher, around 900 AD, about 1100 years ago. Again, that only comes from the geological evidence. Native Americans have oral histories of these things happening, but to get the details and put them into the scientific evaluation, we have to look at the geological evidence, at least for the most part. Although any stories people can tell about these things could help us understand them better. The Untitled Earthquake in 1872, that was felt and experienced. There were people in the area, there were newspapers in Walla Walla and Puget Sound, but in the Untitled Wenatchee area, not very many people lived here. And the reports are not very direct. But for that earthquake, it cracked the ground and broke chimneys over in Olympia and Seattle. That was a big earthquake. Maybe the biggest crustal, shallow earthquake in Washington State at historic time, even though we don't have an exact measure of its energy. All right, so how did geologists, so most of those previous examples come from geological evidence rather than witness accounts. So I'm going to a little bit of run through about how geologists work. So here's Nicholas Steno, who came up with the idea that you could look at the rocks, especially layered rocks, and put together a sequence of Earth history. He wrote in Latin like they did back in those days, and published in Europe. Scientific, this is early science in Europe. His book, and there's a translation in Latin. I'm not going to read the whole thing. So this is back in the 1600s. And Steno first came up with ideas that became founding principles that geologists still use in many ways. James Hutton, Scotsman in the 1700s, wrote a book, The Theory of the Earth, not the easiest book to read, and took Steno's ideas and applied them further and came up with more theoretical insight, you could say. And they're both, these and others developed the idea of stratigraphy, which is you can look at layers of the Earth, and how they're sequenced, younger on top of older, and other things that have cut them or distorted them, and get a record of Earth history in a given area from its stratigraphy, from the geological evidence under the ground. So that's where much of what we know about these earlier earthquakes that we don't have direct witnesses for the Pacific Northwest. Okay. So for the Cascadia great earthquakes, starting with the one in 1700, it was primarily Brian Atwater, who works for the U.S. Geological Survey out of the University of Washington, Seattle, who first got onto this in the late 80s, early 90s. And the story he tells, and he's given talks here in Wenatchee twice in the last 5 years, I think. Some of you might have been there. These ghost forests along the coast. Like this is out near Grace Harbor by the estuary. So it's right near salt water. But there's these dead cedar and other trees. So he went and started wondering what could have killed them. Their roots are down in salt water now, and they're dead. So he used dendrochronology, where you drill into the tree and look at the sequence of tree rings, and you overlap that with living trees, and you come up with when they died. And he worked with a dendrochronologist who measures tree ring ages and so on, and David Yamaguchi, and they kept coming up with around 1700. So the thinking was, in 1700, the level of the land abruptly dropped and put the marsh here with trees in it down so the roots were in salt water and killed them. And there's a bunch of dead forests along the coast from Northern California up to the Vancouver Island coast. So they were wondering if this is a connection, and there was a really huge earthquake. Here's Brian Atwater looking at some layers. So now we're getting to the stratigraphy going down deeper. Here is a dead marsh layer, the layer of sand on top. This is from 1700 earthquake, where the marsh, okay, so the theory is that there was a marsh here, above sea level, relatively fresh water. All of a sudden, an earthquake occurred, the land level dropped, and a tsunami washed a bunch of sand in. So the bottom part of the sand is from the tsunami deposit. I'm not sure if the whole thing is. The sand includes little fossils that come from further offshore, showing it washed in from beyond the beach. Anyway, so the idea is this is a tsunami deposit, at least the base of this sand is. The land level changed because after this, it stayed in salt water, although since then the coast has been gradually lifting back up. So there's a sequence here. Earthquake occurs, it drops, a tsunami washes in, and then years go by and it gradually lifts back up again. And then it repeats again, and there are a number of layers like this, dead marshes, sometimes with tree roots and tree trunks in them, followed by a coarse sand layer, followed by finer sand, until finally it comes up above sea level again, and the marsh grows again, and then it happens again. So now Atwater and others, and it's not just him anymore, have done radiocarbon ages on the older ones, and they got it back 6,500 years, and they've got more than 10 of these great earthquakes So they're happening on the order of every 500 years apart. That's a really rough average, because it varies from 200 to almost 1,000 years in between these major earthquakes that they can find evidence of up and down the coast. Okay, so the last one, so take the rough average, 500 years from this type of study, and the last one was in 1700, and it's 315 years later. It's building towards the next one. We don't know when it's going to be, but we can see it building that way. We can measure that the fault is locked, the Great Megathrust Fault, and so on. So that eventually it'll happen again. Now it might only break part of subduction zone at once. It might only be a magnitude 8 or something instead of a magnitude 9. We don't know in advance. In fact, the evidence is only about half or 2/3 of it is locked right now. So maybe it'll still be a serious earthquake if it's 8 or 8.5, but we'll, I don't know if I'm gonna be alive when that happens. It might be a couple centuries from now. It'll be interesting to see. So since this knowledge came out from the 1990s on, it's been taken more and more seriously, including by FEMA and Washington State and the Washington State Superintendent of Public Instruction and all the counties. So here's a model that was put together with calculations for if a magnitude 9 earthquake happened and basically the whole megathrust broke at once. And this is a really cool interactive map you can go to and change the scale. You can look at details like where the tsunami will overlap with land and that sort of thing. But this is the one that happens out on the coast. So this is damage. The different colors, the hotter colors are more damage. So where it's getting up to intensity 8 damage, the red, that's really serious damage. The weaker buildings or certain buildings will collapse, bridges will break, some of them. And you can even look up county by county in the details here if you play with it. How many bridges are estimated to break in each county, how many buildings and schools are estimated to fall apart, etc. And it drops down as the damage is strong in the Puget Sound area as you get away from the earthquake. But even in eastern Washington, there's, what does it say, moderate. There's a moderate effect, and we're not sure, we would feel it. We would definitely feel it here, probably everybody in Wenatchee. Whether it would break into chimneys or anything, maybe. You can't say for sure. I can't say for sure, but you can look at the model and see what it came up with. But probably not too serious, probably not fatalities. I can't promise you that. East of the Cascades from an earthquake like this. It's mostly out on the coast. Now, here's a question. Speaking of tsunami, what about Seattle and Puget Sound? The models and calculations show it would taper out too much by the time it got there to be a significant tsunami. So Seattle will not get hit by a tsunami, but there could be, nonetheless, a surging of water flowing in the harbor that could damage boats and docks. It's kind of like, not quite a tsunami, but a surge in the current in Puget Sound. It doesn't come way out, but it does flow fast for a little bit. So they expect some harborside damage from the flow, where they call it a tsunami by the time it gets to Seattle. Anyway, that's the model. Partly this is based on looking at those other earthquakes that have happened, like in Alaska and so on. Partly it's just based on engineering calculations about how the crust is affected. And also the details, if you blow the scale up, I'm not going to, I don't have it here for you. You can see where the soil is weak, where they expect liquefaction to occur in Aberdeen or Seattle, all that. It's a pretty detailed scenario they got worked out here to use to plan on an emergency and also preparedness basis for an earthquake like this. So let's move into that's the coast. I don't know when the next one will happen, but something like that will happen again within a few centuries is the expectation. Maybe tomorrow, maybe next century. Seattle Puget lowland, okay, it has damaging effects from those coastal earthquakes, even though it's not right there on that version of the coast. But it has its own fault and earthquakes underneath, the deep subduction ones and the shallow crustal ones. They'll go up to magnitude 7 plus or minus at their most severe earthquakes. These are all deep earthquakes. These historic ones above magnitude 6 in Seattle. Those are all the deep type in the last 100 years. Okay, centered down South Puget Sound, Olympia in 1949, 1965, and then Nisqually 2011. I think we're lucky nobody was fatally injured in 2001 from the Nisqually earthquake, because it did knock down some walls and things. Previous to above magnitude 6.5 earthquakes, one of them killed 7 people, one of them killed 8 people. So the greater Seattle Puget Sound area has had fatalities in the last 100 years, up to 7 or 8 in an earthquake. Those are the deep ones, and they'll continue to happen. They happen every few decades, apparently. We can't predict exactly when. And then there's the shallow ones, the faults up in the crust, not very deep. And I'm just going to pick the Seattle or Seattle-Bremerton fault as an example. Because that's another thing that geologists and nobody knew about much. I mean, they thought there might be a fault here by the geology of Seattle, but it wasn't until Atwater led the way again and started making discoveries kind of like he did down on the coast, but in the Puget Sound area around Seattle, that it was figured out that there was apparently a major, like 7 to 7.5 magnitude earthquake about 1,100 years ago on the Seattle fault, big enough to generate a tsunami within Puget Sound. Now, we don't know how often earthquakes like that happen on the Seattle fault. It's been over 1,000 years, so we're hoping it's going to be at least that much longer. And in detail, so it runs roughly along Interstate 90 from Issaquah through the industrial sports stadium district, underneath there, and over towards Bremerton. And Seattle does have a lot of wet, muddy ground and artificially filled ground, which tends to move a lot and maybe fail during earthquakes more than solid rock ground does. I mean, definitely more. In detail, it's a multiple strand fault, so they call it a fault zone. And there's been microquakes or even up to felt level quakes in the last 20 years, more or less the Seattle fault zone, but nothing major. But because of what Atwater discovered, where, see the south end of Bainbridge Island, West Seattle, it's a thrust fault, or actually it's more of a reverse fault. It's a pretty high angle fault, and the rocks on this side, they got thrust up like that above the rocks up here. So that you can see a lot of bedrock around Puget Sound in these areas. You get up to here, and the bedrock's buried deep under younger, softer sediments that have filled in more recently, the Seattle Basin. That's because of this fault zone that keeps pushing this part up during a major earthquake. It's been happening for a long time. So that's one, and there's other earthquakes around the Puget Sound area that each have their own story and can each produce maybe up to magnitude 7 earthquakes. Just not so often as some of these others we're talking about. But we don't know the timing. And I don't have the details of what we do know on that part. Okay, they ran a scenario for if the Seattle fault broke, magnitude 7.2, about like it did 1,100 years ago, then the Seattle, Bremerton, Central Puget Sound area would be seriously, suffering the effects of the ground shaking and so on. And a tsunami along the coast of here, possibly, in Puget Sound. So that's a concern. But jumping to eastern Washington, here's the Cascades, here's the Columbia Plateau or Basin. Wenatchee is about here. Well, this map is from Brian Sherrod of the U.S. Geological Survey. In his own different way from Brian Atwater, he's been discovering more about faults and their activity based on the geological evidence. And he's been working partly in eastern Washington lately and then covered some things. But this is a map he put together, and he's using slideshows, and he shared with me. The blue is folds that are still actively folding. When the earth is getting stressed, the rocks may bend and fold, and then ultimately they may break. So he calls these tectonic folds the blue. And then the red are faults that he thinks are active faults. So these are based on Brian's judgment, Brian Sherrod. And this area is thought to be encircled where the great earthquake, or technically it's called a major earthquake of that magnitude, of 1872 occurred somewhere in this circle. So he went, and geologists have been wondering, where the heck is that fault? For decades. He went looking for it, and he had a tool. Well, let me back up a step. Here are epicenters, locations on the Earth's surface. Here's the Olympic Peninsula, Puget Sound, eastern Washington, Wenatchee. There's this zone up north of Wenatchee, here's Lake Chelan, called the Chelan-Atiat seismic zone that gets a lot of earthquakes. A cluster. Every year it gets a few. Now most of them are small and not felt, but sometimes people feel them. Okay, so and the thinking is it's probably somehow related to the earthquake of 1872. It's fault is in there somewhere. And also the descriptions people gave. The movement and the damage, even though there wasn't much built human structures of damage back then, was in here somewhere, where that earthquake was centered in 1872. By the way, here's Brian Sherrod in the red up front, in the trench, in what he thinks, cuts across what he thinks is that fault. Well, and it sounds like he has, pinpointed where that fault is, instead of just knowing it's in that general area somewhere. By the way, here's a story. When they were trying to decide if they were going to build a nuclear power plant back in the 1970s on the Cascadia River, this is one of the few above or around 1907 earthquakes they knew about that had happened in Washington State, but they didn't know exactly where it was centered. So people that didn't want the nuclear power plant over here said it happened over here. People that didn't want it over there said, oh, it happened over here. Because they weren't going to build it too close to a fault like this. So they kind of kicked that one around a while. Now here's a tool that Brian Sherrod had that's more recently developed. This is called the LiDAR image. It uses, what they do is, and it really shows in detail the shape of the Earth's surface, getting rid of the effects of vegetation, which is often important to get around and really see the shape of the Earth's surface. And it uses laser reflected off the Earth's surface to an airplane flying over. And it costs a bit of money to do this. But this is a LiDAR image. Okay, here's the Columbia River flowing north. Etihad is a little ways up here. This is Orondo in here. So right across the Columbia River, pretty much from Orondo, is this canyon, Spencer Canyon up in here. And so here's a ridge separating these three ranges in here from the surrounding areas. There's some logging roads, the white thing. This is a landslide that came down the stream. Came out of this scarp up here, landslide, headwall scarp. And you can still see the irregular ground to the left. And there's another landslide here. But anyway, Brian Sherrod actually asked for this LiDAR to be run because he looked at an earlier one that didn't show as much detail and he thought he saw something. So they paid for this LiDAR analysis and he spotted this, which is a scarp, a little miniature cliff that runs along the Earth's surface. It's only 3 feet high or so. But that shadow there is this scarp that breaks, cuts through. Now, not all scarps are necessarily faults, but when a fault breaks through to the Earth's surface during an earthquake, it creates a scarp. And if not too many years have gone by, it's still there and hasn't been eroded away. So we went up there to look at this thing. And it runs. If you look really hard, you can find it going out of view here. He has it up to more than 3.5 miles of extent now. If you add up how much it moved and how long it is, you can estimate the magnitude of the earthquake, and it's 6.5 to 7.5. Okay, and there are dead trees on, let's see. Well, the landslide killed some trees, and then trees grew on the landslide. And doing tree ring counting, and assuming these landslides were caused by the earthquake, the tree deaths were caused after 1850 or so, and the new trees started growing towards 1880. It's 1872 is in the middle of when this must have happened. So he has a fault. It moved the right amount to create the right magnitude earthquake, and based on the trees that were killed, it happened in the second half of the 1800s. So he's confident now that this is the fault. He calls it the Spencer Canyon fault, and this is where the 1872 this is the effect of the 1872 earthquake. The fault broke through here. It's another thrust fault, and the rocks up here. Let's see if I have this right, Kelsey. They climb up and down towards the south, more or less. So there's compression squeezing the crust here. The rocks occasionally break and the crust climbs up on itself along the thrust fault. Or if it's steep enough, that would be a reverse fault. So, knowing about that earthquake from 1872, ever since 1872, even before Brian Sherrod's discoveries, they ran this scenario for what if it broke again like that, somewhere near Etihad. And now Wenatchee's down here, so this is just a model based on the best science that these groups could come up with a couple of years ago. So that would be very strong damage to strong damage, which would be, if this happened at that magnitude, somewhere up toward Etihad, there would probably be fatalities, there would be broken buildings, etc. It would be of serious concern based on models like this. And based on what happened in 1872 when there was hardly any structure around to show the effects. So that's our local concern. Sherrod and others have found faults, I should have pointed out on the earlier map, across the Yakima Fold Belt, some of which are active, and some of them go beyond into the Cascades. Now the Cascades are a little bit needing further exploration. We don't know the faults and which ones are active up there quite as well. There's more to learn, but I'm just telling you what we know so far. It's enough for concern. And by the way, that trenching method, Sherrod digs into what he thinks is a fault, and he looks at the stratigraphy and the structure on the sides, and to see if there's a fault there that shifted things. And if it works out well, he can find things to radiocarbon age or do other kinds of age measurements on. And he's been doing that for the last year and more to the Spencer Fault. He does a trench across it. One of the people here have been there. Because one thing about geologists like Brian Sherrod, they have trench open houses to come and look at the fault they've discovered, or the possible fault they've discovered. So yeah, bring a shovel and bring a hard hat. But anyway, he thinks, well, he hasn't published the full paper yet, which I'm eager to see, where he has further age evidence and so on to show that this was the 1872 earthquake fault. But he hasn't changed his story, so I think that's going to turn out to be the case. But anyway, elsewhere in eastern Washington are other faults that have been active in the last 10,000, not to geologists, that have been active in the last 10 or 12,000 years. That's an active fault. Okay, that's pretty recent geologically. Now, Brian Sherrod, I don't know if he'd stand behind this, but during the question and answer, he came to give a talk here a year or so ago. He says, as far as he's concerned, all faults are active. Now, I'm not necessarily backing that statement up. Some I think are inactive. He just is eager to investigate all possibilities. Is my interpretation. But there are other faults that have been shown to be active in the last 10,000 years, all the way down to Walla Walla. Volcanoes had earthquakes of a minor, actually of a magnitude 4 type in the last 10 years. I mean, so eastern Washington has its shallow faults that can have, in some cases, up to magnitude 7 earthquakes. So let's summarize. Go back out to the coast. I mean, this is what we think, and this is what's going to happen eventually. The question is, when is eventually, of course. The coast does get megathrust earthquakes up to around magnitude 9. Like any subduction zone does, it just doesn't get them very often. The last one was in 1700. The damage is devastating to given areas, depending on what exactly happens there, and if it's in the tsunami zone. So there, that magnitude on the coast, that type of earthquake, is going to produce probably a big tsunami.
Which way is it gonna go?
The tsunami, it's going to spread out in all directions.
Okay, so.
It's going to hit the nearby coast first, but if it's that big, it'll hit Japan and Hawaii and coast of Alaska and so on.
Will it swamp them?
No, just the coast, up to 10, 20, 10, 15 feet or less typically, but it varies depending on the size of the waves. I forgot to mention that 1700 earthquake that Brian Atwater discovered the evidence of, and other workers like David Yamaguchi. Someone found in Japan and let them know about there's a historical record of a tsunami hit in Japan in 1700 on January 26th. They called it in Japan the orphan tsunami because they didn't know where it came from. All the major earthquake zones around the Pacific Ocean had people living there at the time that kept written records of things, except for the Pacific Northwest, Cascadia. So by elimination, that would have been the source of that tsunami, which to them was one of the, there's a lot of evidence, more than I mentioned, and more than even that converges on being pretty, to me, totally convincing. There was a great earthquake there in 1700 along our coast, and then the earlier ones as well. But that one only caused a moderate amount of damage in the harbors and the boats and so on. I don't think it killed anybody in Japan. Hawaii often gets them from any direction across the Pacific, from being at the center of the Pacific Ring of Fire and earthquakes. Anyway, okay, great stuff. Now Seattle is exposed to some effect, pretty serious effect, from the coastal megathrust magnitude 9 or so earthquakes. We're going to go see significant damage. I mean, not just slight shaking or something. Possible fatalities, probable fatalities, but no tsunami, except there could be some damage along the docks and the boats tied to the docks, is what the experts say. Seattle deep earthquakes, those have happened historically in the last 100 years a few times. They can cause major damage, like they may shut down the state capitol for a few years to fix it after, like they had to do after the Nisqually earthquake, and more, roads broken and so on, buildings broken. Fatalities are possible and have happened in the last 100 years for those kinds of earthquakes in the Puget Sound area, but no tsunami. And then the shallow faults in the Puget Sound area have not, in historic times, produced magnitude 7 earthquakes, but now we know that they could. And if they did, like under Seattle, Seattle fault, that would be worse than one of these. If a magnitude 7 happened on the Seattle fault, that would be more. They estimate well over 1,000 fatalities if that happened on that scenario. And an inside Puget Sound tsunami was set off before by one of those, so that might happen again in the worst case. And then let's look at eastern Washington, as represented by Wenatchee. We would feel a megathrust earthquake out on the coast, but probably minor damage and hopefully no fatalities. Casualties. We might break mirrors or maybe even chimneys. Brick that isn't reinforced is particularly vulnerable. We're way away from the ocean and way up in elevation, so we're not going to get a tsunami over here. Now, deep earthquakes don't happen under us, but they happen under the Puget Sound country. And like this fall, like 2001, we had minor or no damage. Nobody was hurt over here, and there's no tsunami over here from any of these. But then there's our local ones, like the one up by Entiat. So that's the big concern around here, really. I mean, yeah, we may get some damage, and we're not sure about casualties from the big coastal earthquake here in Wenatchee. But it's the ones in our local crest that are that can do greater damage when they happen again up to magnitude 7. So major damage, and like if it was the Entiat, area fault, maybe damage from here to Chelan and beyond.
How many dams do you think?
Well, see, they don't think any. According to
Oh,
the PUDs, keep studying this, and they know about, they've known that it was up around magnitude 7 in 1872 since before they built the dams. So they've taken that into account, and every time advances are made and people like Brian Sherrod publish more papers, they reevaluate, and so far they're still confident that they can withstand up to magnitude 7 or so earthquakes around here. But I'm just going by what they say. But you know, they're pretty good engineers. So. Fatalities would be quite possible, probably likely from an earthquake that big near a town over here, and again, no tsunami. I'm not going to take time to talk about a siege, which is a wave inside a lake or reservoir set up by the earthquake waves in a different way from a tsunami, but we're not going to go there. So, if anyone live on Lake Chelan, you can look into those. Yeah, okay. They're usually pretty nice. All right, anyway, that, I think, oh yeah, conclusions. Now, as a geologist, I said based on the latest science, that includes a lot of geology. What I'm trying to say here, I'm trying to bring it pretty up to date, what we think is going on. This is a quote from one of the FEMA and other reports, future earthquakes are inevitable in each of these places. The timing, though, is questionable for how long it is till the next earthquake. That's the story we have to look into separately. But it's best to be prepared. And there's been a lot of preparation done in this state. Just a month and a half ago, there was a Great Washington Shakeout they've done 4 years in a row. They get more people in Western Washington to sign up for these things where they practice emergency drills in the case of an earthquake. And on from there, there's a lot of planning and some preparations been done. Building codes have been changed since the 70s and so on. We should keep working on that. And also, like what I'm trying to do, keep educating people and keep public awareness so people aren't totally surprised, or at least have some idea what to do and what's going on when one of these happens and it affects where they are. And then we still don't have all the answers and we haven't found all the faults, so I think more research is needed. And that's my talk, and I'll take questions. So, questions?
Yeah. Number 4, so in Chelan County itself, down the river, Wenatchee, how many seismometers actually in place?
Don't know the answer to that. The Pacific Northwest Seismic Network has a number, and they have a map showing where they are. But I don't know. Anyone else have a handle on
There's one at the south end of Lake Chelan on the DOT building, and you go down towards Chelan Falls.
The more,
That might be the main one up at Chelan.
yeah, the more seismometers, good quality recent ones in the network we have, the better for measuring what happens.
Yeah, and
I just don't remember.
I'm not certain if we have one around here. I do know that one because I didn't see it, but I don't know.
Yeah, I don't know, to tell you the truth. There's some local ones, but not that many, I think.
I was just wondering, because we have North Atlantic faults here, where we have the fault block is dropped.
Yeah.
It just seems like,
Well, so you're talking about the Leavenworth Fault and the Antiac Fault. Those are geologic structures that are generally called inactive. Like no evidence of earthquakes on them, at least in the last 12,000 years, and probably a lot more. Now, Brian Sherrod might say we should still keep an eye on them. So, or they're worth investigating to make sure they haven't been active for a long time. In his view, I maybe. But anyway, that's the future research. The Antiac Fault, unlike the Antiac Fault actually runs into the north end of Wenatchee up by Omi Gardens. So if that were active, that would be a serious concern, starting with the Sunny Slope area. But again, geologists have long called that inactive because they have evidence of geological things that cut across it that are kind of old, that have not been offset or cut by the fault, suggesting it's been inactive for that long. Okay, see what I mean? So one way to approach it, besides looking for more geology along the fault to see if it's moved anything in the last however many years, is to get more seismometers and measure the details of the local area as far as future research goes. Yeah.
Your chart where it was showing these different earthquakes in different areas in the state. And the one where it was a local quake in Seattle, and it was shallow.
Yeah.
And the chart says tsunamis are not likely. I don't understand if you've got a shallow quake that is at a magnitude of 7, I don't understand why Puget Sound and Lake Washington wouldn't just churn.
You might be right, and maybe I shouldn't have said anything there about really being able to estimate the odds. We only have one example, I think, still so far, of a tsunami within Puget Sound, and that's from the one 1,100 years ago on the Seattle Fault.
That gave you
And
help.
whether that represents what happens each time there's a magnitude 7 on a, and that was right under Puget Sound, where most of the motion was. So maybe you might be right in thinking anytime there's movement up around magnitude 7 on a fault that cuts right into Puget Sound, it's likely to produce waves. Yeah,
Well,
that could-
on that quake, I mean, 1,100 years ago, that's when the uplift gives
Yeah.
you Alki Point. That
Okay.
has to displace water.
That particular scenario does have a tsunami.
Yeah.
But I was, in my summary slide, maybe not very carefully done, I was trying to incorporate all that shallow active faults in the Puget Sound area, some of which don't go into Puget Sound. So in that case, it would be unlikely. Yeah.
So I was in an earthquake in the northern Chilean Andes in 1972, in a town called San Pedro de Atacama. This is in an intermontane valley. It's, as you're probably aware, the Atacama is very dry, so groundwater is way down. And the locals there say that in the mining towns like Chuquicamata and Calama, the earthquakes are always more severe than on the towns on the sediments. Is that related to the sediments being dry there?
Well, it partly relates to where the earthquakes are happening. Was this relatively local in the Andes?
Those are earthquakes along the Atacama Fault Zone, or the Domeco Fault Zone in Chile. There's two big linear fault zones in northern Chile. One is the Atacama, which is near the coast, and further in, and the other one is further inland. So there's the two major fault zones that are in Chile.
This would be the inland one.
Well, they're both Domeco and Atacama are parallel to one another, and that's where all the big mineral deposits are. I'm a geologist, I worked there, and I've been through a number of earthquakes in Chile in the last 15 years.
So is that true what they were saying though?
Well,
Because they're saying in San Pedro that the ground just sort of.
well, San Pedro de Atacama is the big salar there. It's like
Right.
3,000 square kilometer salar, big salt lake is what it is. So yeah, it's because the sediments are
So that they're much likely to liquefy if they're
well,
recently dry, or is it just?
well, it's pretty dry there,
circumstance?
yeah. But there is still water in that lake there, but it's all salt water. My question is that, have they recorded any quakes, any small ones along the, in this area where this geologist is looking at in Spencer Canyon? Because I live up the Entiat, and there is a swarm area near what they call Ferris, which is 5 miles up. And we've had about 4 or 5 of those earthquakes, 2.5, 3. You can feel them in Dickman Canyon. And there is a structure there between that separates what's south of what's downriver from the Roaring Creek, and the Roaring Creek terrain, which is a reverse fault, or a flip-in, I think they call it. And so there's this abducted terrain inside there that has a significant fault. I mean, I could walk by my folks' property, and that fault you can extend it all the way across the valley and over through Oklahoma Gulch. And so, because you can see what appears to be a fault zone there, so I'm curious as to why he hasn't, why there haven't been any earthquakes, or I haven't heard any being centered around where this guy says it is in Spencer Canyon.
Yeah, I kind of have to put it that way. We have to ask Brian and some
Yeah.
seismologists for more information on that. My sense, without being an expert on the Chelan Entiat seismic zone, there's a whole network of faults in that area. I mean, it's a real fault zone. It's
Yeah.
a nexus of faults.
Because once you go above if you look at the rocks as you drive up north of Earthquake Point, it's this migmatite zone that separates the rocks down here, which are more like the Swaking complex, whatever they call it.
But what's of interest is we don't know other faults besides what Brian's calling the French earthquake, the
Yeah.
Cascadia fault, have the potential for the bigger earthquakes. Or if that's sort of the master thrust fault in the area, maybe,
Yeah.
maybe not. Maybe others could break in other places.
Because it just looks like, I mean, the rocks are all caught up in there. And there is a fault, you can see it as you make the turn there at Spencer Canyon going south. If you look at the outcrop there on the side of the road, you can see a shear zone in there. It's probably about 5 or 6 feet wide. You can see the myelinitic zone right there.
One thing we have to do at some point is just keep taking the phenomenological approach. Earthquakes happen here, we see faults here. We don't have an explanation for all of them, we don't see all the faults yet. But here's the record of what happens, both from recent seismology and from history, and prehistory. Any other questions? Yeah.
I just wonder if you might comment on what type of earthquake and magnitude would likely get the volcanoes going.
Well, there's only a slight correlation between earthquakes and volcanoes, and it usually takes big earthquakes.